All right, so today we're going to talk about section 6 in chapter 1, polynomials and rational functions. So how can we tell if something is a polynomial? Let's start there. Basically, we have this formula here, but I think that usually is confusing to people. So I'm going to try to break it down a little better. So first of all, polynomials are always of the form. So each term is of the form ax to the n, where a is a real number. Basically, everything is a real number that you will have to deal with. Okay. A is a real number, also called the coefficient. Okay. And n is an integer, but that integer has to be greater than or equal to 0. So what is an integer? An integer is a whole number. No fractions, no decimals. It is just a whole number. And we call it, and it is called the degree. Okay, so this I would say is very important, and we do have to understand all these pieces. So, for example, let's say we have 3x squared. Is that a polynomial? Well, sure. 3 is the coefficient, and it is a real number. And 2 is the degree, and it is greater than or equal to 0, and it is a whole number. If I were to say 3x squared plus 2x, now we really do have two coefficients. So 3 and 2 are coefficients. But we still have a degree of 2. The degree is always the largest exponent. And we can also say here that 3 is the leading coefficient. Okay? And then let's do one more. Let's say we have 3x squared plus 2x plus 1. Well, we have 3 coefficients. We have still a degree of 2, but why does this 1 fit into this form? It does because 1 is the same as x to the 0 power. So for 1, our degree equals 0. Basically, what they're saying is that if I were to have our 3x squared plus 2x plus 1, then 3x squared, comma, 2x, comma, 1 are terms. They're just any piece of the sum of all of them. The leading term is the term that contains the highest power of the variable. The term with basically, for our example, our leading term is 3x squared, and our leading coefficient would be 3. Because of the definition of leading term, we often rearrange polynomials so that the powers are descending. That's basically what this says. This right here, notice it starts with x to the n, and it ends with a constant with no x, and the ends are decreasing. Okay. Let's do our first example. Identify the degree, leading term, and leading coefficient of this polynomial. Well, it's not in standard form. Let's rearrange it because they're asking us a lot about degrees and leading terms and leading coefficients. So we're going to rearrange this to minus 4x cubed plus 2x squared plus 3. Once we do that, it's very easy. So the degree is equal to 3, the largest exponent. The leading term is equal to minus 4x cubed because it's the beginning. It's the start when we put it into standard form. And the leading coefficient is equal to -4. Remember, it's the A. A is the real number called the coefficient. And the leading one just means the first one. Okay? So that's really all there is to that. So we want to talk about different behaviors and intercepts. As with any function, the vertical intercept, also known for us as the y-intercept, can be found by evaluating the function at an input of x equals 0. So in layman's terms, when x equals 0, we find the y-intercept. And of course, we call it vertical and horizontal because the axes are not always called x and y. Since this is an evaluation, it is relatively easy to do for a polynomial of any degree. To find horizontal intercepts, we need to solve for when the output will be 0. So that's a little bit more difficult. So this is y-intercept, and what the other saying is when y equals 0, we find the x-intercepts. Okay? That's what all that says with vertical and horizontal. So we're going to limit ourselves to 3 possible cases. Case 1, the polynomial can be factored. Okay? We'll see that. The polynomial is already factored. It's given in factored form. And the last is we really can't factor it. It's really hard to do. So what we're going to use is technology. Okay? Graphing calculators. There's lots of graphing calculators on the internet. There's ways to find these intercepts pretty easily on the internet. So, case 1. Find the horizontal intercepts. Basically, we're saying y equals 0, and we want to find x. First step always is find the greatest common factor. So if I look at all of these, there's no numbers that are in common, but they each have x squared as their greatest common factor. So first step is I can say this equals x squared times x to the fourth minus 3x squared plus 2. Okay, there we go. Now we want to factor this right here. And if you don't know how to factor that, notice that, and I'm gonna use something we call substitution. Okay, I'm gonna say let's let u equal x squared. Okay, you'll see why in a minute. I'm only going to look at this right here because x squared is already factored. And I can say that means that this is u squared because u squared is equal to x squared squared, which is x to the fourth, minus 3u plus 2. And once I get it into this form, I can actually factor it pretty easily. This is u minus 2 times u minus 1. And if you put those, if you FOIL those back together, you'll see that we actually factored it. So now I'm going to go back here and I'm going to say this equals x squared times, well, u is equal to x squared. So I'm going to just plug that back in and I get x squared minus 2 times x squared minus 1. And then we look, can we factor those? Well, both of those are the difference of squares. And I know you're not used to seeing it like that, but we have 0 equals x squared. And this could be x plus the square root of 2 times x minus the square root of 2. And this is x plus 1 times x minus 1. So the difference of squares, if you forgot, says that if I have a squared minus b squared, that equals a plus b times a minus b. Very important to remember. So if I'm looking at x squared minus 2, if I'm looking at x squared minus 2, I'm saying that a is equal to x, or a squared equals x squared, which means that a equals x, and b squared is equal to 2, which means that b is equal to the square root of 2. So that's how I can factor all of that. To wrap everything up, we have all these factors. So find the horizontal intercepts of f of x equals x to the 6 minus 3x to the 4th plus 2x squared. We've factored it as much as we can, which means that I have x equals 0 as one of my horizontal or x-intercepts. I have x plus the square root of 2 and x minus the square root of 2, which gives me x equals plus or minus the square root of 2. Those are two more solutions. And last, I have x plus 1 and x minus 1, and that gives me x equals plus or minus 1 as my other solution. So I actually have 5 solutions to this polynomial. And of course, horizontal intercepts, x-intercepts, and solutions, and zeros. We say all of those mean the same thing. Okay? All right. Now, for this next question, we have t cubed. H of t equals t cubed plus 4t squared plus t minus 6. I can tell you right away, this is not factorable. The only techniques that we have to factor this are factor by grouping, and I promise you it will not work. Since it's not in factored form, we do need to find some way to graph this, okay? How would we graph this? Well, there's a few calculators out there online, or else you have one in your possession, but we have, there's a Desmos graphing calculator. There's GeoGebra, which is also a graphing calculator. Okay, so I have my function is, and I'm just going to write y equals, because this is obviously used to x's and y's. So we'll say x, I'm pressing shift 6, which gives me an exponent, and that exponent is 3, plus 4x to the second power, and then let's see what else we have, plus x minus 6, plus x minus 6. All right, so if I open this up full screen, I can actually see I have an intercept here at minus 3, 0, minus 2, 0, and 1, 0. So I have found all my intercepts, and that should be exactly the same, which it is, for this graph. So using a calculator works very well. We could also check these numbers by plugging them into our original equation and making sure it's equal to 0. But if we can't factor it and it's above a quadratic, which means that the degree is higher than 2, we really do need to break out a graphing calculator. Okay? So if I want to solve polynomial inequalities, one application of our ability to find intercepts and sketch a graph of polynomials is the ability to solve polynomial inequalities. It is a very common question to ask when a function will be positive and negative, and one we will use later in this course. So I'm going to use a number line, okay? So here we have this inequality. And the first thing I really want to do is I just want to set it up as an equality. Because what I want to do is I want to find what my zeros are. So let's just say it equals 0. Okay? That means that either x plus 3 equals 0, or x plus 1 equals 0, or x minus 4 equals 0. Because if any one of those factors or any one of those multipliers is 0, then the whole thing is going to be 0. So here we get x equals negative 3, x equals negative 1, and x equals positive 4. Okay? And the easy way to do it, and I know that there's people who do it differently. What I do is I say, we have to pick a number in each interval. So let's pick -4 for this interval. Okay. So if I have x equals -4, and I'm going to plug it in to x plus 3 times x plus 1 squared times x minus 4. Well, I don't really care what the value is. I really just want to know if it's positive or negative. So here, when I plug in -4, this becomes a negative number. No matter what this is, when I square it, it's always going to be positive. And then here we have -4 minus 4, again, a negative number. And when we multiply a negative times a positive, we get a negative, times a negative, we get a positive. So that means this interval has to be positive. And I think this makes it a little easier than worrying about what our values are, okay? Let's do the same thing here for -2. So when x equals -2, we have x plus 3, x plus 1 squared, and x minus 4. So -2, well, this is positive. This is always positive, and this is negative. So that makes this negative. Another number I'm going to plug in, and again, I'm going to try to pick easy values. Here, this time, I'm just going to plug in 0. So I have, when x equals 0, I have x plus 3 times x plus 1 squared times x minus 4. And this gives me a positive, always positive, and a negative. So again here, this is negative. And last, let's pick 5. So we get when x equals 5, x plus 3, x plus 1 squared, and x minus 4. Well, this is a positive. This is always positive. And now this is positive. So my entire region is positive. When this is greater than 0, which means we want to know when it's positive. So our polynomial is greater than 0, well, when it's positive. So from -infinity up to -3, not including -3. Also from 4 to positive infinity. And we just put a union between them. When we have these intervals, we put a union, which means it's like adding those two. We're taking those two intervals and adding them together. Okay, so that would be the solution to this equation or this inequality. All right, next. Now we're going to talk about rational functions. So rational functions basically are polynomials over polynomials. Rational functions are polynomials over polynomials. And now we know what the rules are for polynomials. So as long as we have one polynomial over another polynomial, we have a rational function. Okay? So you plan to drive 100 miles. Find a formula for the time of the trip, for the time the trip will take as a function of speed. Okay? So we want time as a function of speed. So we start off with a formula that you may or may not know, which is that distance is always equal to rate times time. How can you remember that? Well, let's think about it. So if I were to drive, this is rate, and we'll call this miles per hour. This is time, and we'll say this is in hours. And we'll have this as distance in miles. Okay? So if I were to drive 60 miles per hour for 1 hour, we would go a distance of 60 miles. If I were to drive 60 miles an hour for 2 hours, I'm going to drive 120 miles. If I go 60 miles an hour for 3 hours, I'm going to go 180 miles. So you can see that distance equals rate times time. Okay? Now we want to solve this for time. So how do I solve this for time? I divide both sides by r, which gives me d over r is equal, these cancel, I get t. So I want t as a function of speed, which is our rate. That equals d, which I know already is 100, divided by r. So I found a formula for the time a trip will take as a function of the speed you drive. So here it says, notice that this is a transformation of the reciprocal toolbar function, f of x equals 1 over x. We learned about f of x equals 1 over x. Several natural phenomena, such as gravitational force and volume of sound, behave in a manner inversely proportional to the square of another quantity. For example, the volume of a sound heard at a distance d from the source will be related by v equals some constant over d squared. These functions are transformations of the reciprocal squared toolbar function f of x equals 1 over x squared. And we've already gone over all the toolbar graphs, right? This is 1 over x, and this is 1 over x squared. I just put those here to remind you. So our function that we found is t of r is equal to 100 over r, which is really the same thing as saying 100 times 1 over r. So we can see that there's a vertical transformation of multiplying all the y values by 100. So if I were to take this graph that I see right here, without doing a lot of work, I can change this to 100, this to 200, this to 300, this to 400, and the graph would look now exactly the same. This would be negative 100, negative 200, negative 300, and negative 400. And if I do this, if I plug in r equals 1, because this is now the r axis, and this is the t of r axis. If I plug in r equals 1, I get 1 over 1, which is 1 times 100 is 100. Notice, there's my point, and so on. We have seen these graphs before. I just showed them to you the last one. But let's point out some things that I think will help you understand how this actually works. So vertical asymptotes. Let's use the function 1 over x. And I'm going to draw it a little strange to help see what exactly is happening. Okay? So we have, let's just say we have y equal 1 over x. This is the x-axis. This is the y-axis. Now, I'm going to do something that's going to look a little strange. It's not going to be proportional. So let's call this 1, and we're going to call this 1. Okay? So when x equals 1, y equals 1. We have our point right here. Okay? Now, let's say x equals 1/2. So 1 divided by 1/2 is equal to 1 divided by 1/2. Keep, change, flip is the same as 1 times 2, which equals 2. So this is 2, and we have a point here. Actually, let's move this one down a little. I think I'm a little high there. Let's call this 1. Okay. And then how about if we say, instead of little by little, let's say right here, and again, it's not going to be to scale. Let's say this is 1/10, and let's say this is 10. So that for the same reason, when x is 1/10, y is 10. What if we pick a point 1 over 1 million? So I'm going to write 10 to the 6th power as 1 million. And then I'm going to write 10 to the 6th power as 1 million. So this is 1 over 1 million. And it's going to be 1 million. And we can see that the smaller the fraction gets, the larger the y value gets. Let's say this is 10 to the 10th power. So let's say this is 10 to the 10th power. Then we have a point here. And what does this graph really look like? It looks like basically like this. There we have it. And we can see that the closer that the x gets to 0, the larger the y gets. And that's what this says. As x, this says, as x approaches 0 from the right or from the positive side, f of x or y goes to infinity. So you can see as x gets closer to 0, y gets closer to infinity. And the same thing is true in the negative direction. Everything I put in here would be negative, and I would have a graph that would do the same thing, just it would go negative because all my values would be negative, right? So as x gets closer to 0, so as x approaches, here, let me write it here. As x approaches 0 from the positive side, y approaches positive infinity. Here, as x approaches 0 from the negative side, y is approaching negative infinity. Okay? And that's basically what all that says. Okay? And hopefully that made it a little more clear. And let me finish by saying that that means we have a vertical asymptote, and it's really just a broken line. We have a vertical asymptote at, and remember I said it's a line, so it is at x equals 0. Okay, so let's define vertical asymptotes. Step 1, factor numerator and denominator. Step 2, simplify by canceling common factors. And 3, set all factors in the denominator equal to 0. That's how we find our vertical asymptotes. All right, so now let's work on horizontal asymptotes. And we're going to do the same thing. We're going to use the same function, y equal 1 over x. Okay? And we're going to do it again a little differently. So this time, I'm going to start with x equals 1. Y equals 1. Okay? And now, when x equals 2, y equals 1/2. Right? Plug in 2, I get 1/2. And then let's get bigger. So when x equals 10, y equals 1/10. I have a point here, I have a point here, and let's make this in red as well. When x equals 1 million, y is going to equal 1 over 1 million. So we have this point. And hopefully you can see that the larger my x values get, the smaller my y values get. And we are going to have the same graph. It's still going to look similar to the one we had before. But what's happening is this is getting closer and closer to 0. Well, can y ever be 0? Let's see. If y equals 0, that's 1 over x. Well, we can multiply both sides by x. X times 0 is still 0. I get 0 equals 1. Obviously, no. We can never make y equal 0 by changing x. But notice we're getting closer and closer. So we have a horizontal asymptote at y equals 0. It just means that the graph is getting closer and closer to 0, but it will never equal 0. And we have the same thing really happening in the negative direction. for the same reason. So let's read what this says. It says, as the value of x approaches infinity, so notice this is getting bigger, x is approaching infinity, what's happening to y? Y is approaching 0. Okay? And in the negative direction, as x approaches negative infinity, y is approaching 0 as well. Okay? And I'm not going to read the rest to you. Basically, I think the picture makes it a little easier to see. This gives us a horizontal asymptote at y equals 0. It's a line, so we call it y equals 0. Now, this, if you notice, has to do with the end behaviors of this graph. We're only talking about what's happening as x gets bigger and bigger and approaches infinity, or smaller and smaller and approaches negative infinity. It's only talking about the end behaviors. In the middle, depending on the function that we have, we can cross a horizontal asymptote. We can never cross a vertical asymptote. Because to cross a vertical asymptote would mean our denominator equals 0. Here we have our definition. Notice polynomial over polynomial. Just make sure that q of x is not equal to 0. Okay, we can never have the denominator equal to 0. Sketch a graph of the reciprocal function. The reciprocal function is f of x equals 1 over x. Okay, and we're going to shift 2 units left. So 2 to the left. That means we're shifting horizontally and up 3. So up 3, which makes this vertical. Okay? Well, on our original 1 over x, we said our vertical asymptote, and I'm going to abbreviate it as VA, is x equals 0. And our horizontal asymptote is at y equals 0. So if our vertical asymptote is normally, if our vertical asymptote is going to normally be right here, and I'm going to shift it to the left, it's going to move 2 to the left, and we're going to get, for our new function, we're going to get our vertical asymptote is equal to x equals -2. We've shifted it to the left. Our horizontal asymptote, which started as y equals 0, is now shifting up 3, 1, 2, 3. So it now is at y equals 3. Notice it's shifting up by 3. This is shifting left by 2. And so those are our new asymptotes. And we just take that graph and we put in our asymptotes first, and then we can sketch our graph. And it's really just a transformation. We talked about transformations in 1-2, or I believe. And so that's how you would do this graph. What does it look like? Well, first, here's our sketch. Should we try to figure out what the function would actually be? Let's call this g of x. So g of x is going to equal f of x plus 2. If you remember, it always goes opposite. And then we're shifting up 3, so we're adding 3. Let's write this as our equation. So we have g of x is equal to f of x plus 2, which is 1 over x plus 2 plus 3. And if I want to write it as one fraction, we get a common denominator, which is x plus 2. And we can combine our numerators now. This is the same as 1 plus 3x plus 6 over x plus 2, which we can say is 3x plus 7 over x plus 2. And this is what this right here, g of x, is the equation for our new shifted function. All right. So vertical asymptotes of rational functions. We really talked about this already. It says the vertical asymptote of a rational function will occur where the denominator of the function is equal to 0 and the numerator is not. Basically, we talked about that. We factor, we cancel our factors, whatever's left in the denominator, we set equal to 0. That will give us our vertical asymptote. We didn't really talk about how to find horizontal asymptotes. So these are the rules that will work. I don't think I'll explain all the reasoning why. If you're interested, please feel free to come to my office hours or make a time where I could show you. But I think that most people just like and have already learned these rules. If the degree of the denominator is greater than the degree of the numerator, we have a horizontal asymptote of y equals 0. So for example, if we have 1 over x, the degree of the numerator is equal to 0. The degree of the denominator is equal to 1. The denominator is greater than the numerator, so we have a horizontal asymptote at y equals 0. If we have, so the degree of the denominator is less than the degree of the numerator. Let's say we have 3x squared over 5x. Let's add these in. Well, here, the degree of the numerator is equal to 2. and the degree of the denominator is equal to 1. So we know the degree of the numerator is greater than the degree of the denominator. We have no horizontal asymptotes. And last, if they're equal. Let's say we have 3x squared plus 5x plus 7 divided by 7x squared plus 2. Well, now we have the degree of the numerator is equal to 2, and the degree of the denominator is equal to 2. So our horizontal asymptote is at y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. So for this one, we would have y equals 3/7 would be our horizontal asymptote. All right. In this sugar concentration problem, we created this equation, C of t equals 5 plus t over 100 plus 10t. Find the horizontal asymptote and interpret it in its context of the scenario. So I have C of t, and what is the degree? Let's change it to t plus 5 divided by 10t plus 100. Well, the degree in my numerator is equal to 1, and the degree in my denominator is equal to 1. So I have a horizontal asymptote at y equals leading coefficient on the numerator is 1, leading coefficient on the denominator is 10. Here's my 10, and we can say that's 1t. So there's my 1/10. So we've found the horizontal asymptote and interpret it in the context of the scenario. Well, this says that the sugar concentration as time gets larger and larger, approaches one-tenth. So as x goes to positive infinity, since we're talking about time, we're not going to talk about negative infinity. My y value, which is the same as the concentration of the sugar, it goes to 1/10. And that's basically what this means. All right, let's find vertical and horizontal asymptotes, and we're going to be done pretty soon. So how do I find vertical asymptotes? Well, I look to see if there's any factors in common. X minus 2, no. X plus 3, no. So all I need to do is look at my denominator. We have x minus 1 equals 0, x plus 2 equals 0, and x minus 5 equals 0. which means we have vertical asymptotes at x equals 1, x equals -2, and x equals 5. These are my vertical asymptotes. Find the horizontal asymptotes. If I were to multiply those two factors at the top together, I would have a leading term of x squared. I don't care about the rest. I would have, and here's a really easy way to do it. Get rid of all the pluses and minuses. Notice now, I can just look, I have x squared over x cubed, which means that the degree of my numerator is less than the degree of my denominator. And I have a horizontal asymptote at y equals 0. And I think that's really probably the easiest way to do it. So I have 3 vertical asymptotes, 1 horizontal asymptote. Okay, find the intercepts. Different question. So if I want to find my y-intercept, that's always easiest, right? Because to find my y-intercept, I just said x equal to 0. When I said x equal to 0, I get -2 times 3 divided by -1 times 2 times -5. This becomes -6 divided by -1 times 2 is -2. -2 times -5 is +10. So here we have negative simplified would be 3/5. So I have a y-intercept at -3/5, and I can say my ordered pair is x equals 0, y equals -3/5. Now for this one, the x-intercept is actually pretty simple because it's already factored. We set y equal to 0. So we end up with 0 equals x minus 2 times x plus 3 divided by x minus 1 times x plus 2 times x minus 5. Now, remember, I can never have, to make something 0, all I have to do is have 0 in my numerator and any number in my denominator, right? Remember, I think I showed you this earlier. If I have a number in my numerator and I have a 0 in my denominator, notice, no. So I don't care about my denominator. All I care about is my numerator. I have 2 values, x minus 2 equals 0 or x plus 3 equals 0. So here we have x equals 2, and here we have x equals -3, which means my x-intercepts are at 2, comma, remember I plugged in y equals 0, and -3, comma, 0. And that pretty much takes care of this entire section. Thanks for watching.